Two engines, same 2-liter size, same fuel. One has 12:1 compression, the other has 9:1 compression. Which one makes more torque? Which one makes more horsepower? And why do race cars love high compression, but turbo cars often reduce it? Let's break this down properly. What compression ratio actually controls? Compression ratio is the ratio between maximum cylinder volume (BDC) and minimum cylinder volume (TDC). Higher compression means the air-fuel mixture is squeezed into a smaller space before ignition. When you compress a gas, pressure increases, temperature increases. That means combustion starts at a higher energy state and combustion efficiency improves. More efficient combustion equal to more useful force on the piston. How it affects torque? Torque is directly related to cylinder pressure. Higher compression increases mean effective pressure inside the cylinder. More pressure pushing down on the piston equal to more torque at the crankshaft. That's why two naturally aspirated engines with same displacement, the one with higher compression usually produce more torque. It extracts more energy per combustion cycle. This also improves low and mid-range response, throttle response, fuel efficiency under load. How it affects horsepower? Horsepower equal to torque into RPM. If compression increases torque, it automatically increases horsepower potential. Also, higher compression improves thermal efficiency. So, less fuel energy is wasted as heat. More is converted into mechanical work. That's why high-performance naturally aspirated engines often run 11:1, 12:1, even 13:1 compression ratios. Because they want maximum power without forced induction. Why not just increase it forever? Because petrol engines face a limit. Knocking. When compression gets too high, fuel can ignite before spark. This causes detonation, power loss, engine damage. So compression must match fuel octane rating, combustion chamber design, ignition timing. There is always a safe limit. Lower compression. Why performance cars still use it? Now here is the interesting part. Turbocharged engines often use lower static compression. Why? Because boost pressure increases effective compression. If a turbo engine already compresses intake air and you also use high static compression, cylinder pressure becomes dangerously high. So manufacturers reduce static compression to allow more boost safely. Lower compression plus higher boost can produce far more power than high compression naturally aspirated engines. That's why modern performance cars prefer turbo setups. Here's something many people miss. Static compression ratio is just a geometric number, but real performance depends on dynamic compression ratio because intake valve closing timing affects actual compression. If intake valve close late, some mixture escape back into intake, reducing effective compression at low RPM. That's why camshaft design changes performance dramatically. Compression ratio works together with cam timing, volumetric efficiency, airflow design. It is part of a bigger system. If both engines are naturally aspirated, high compression equal to more torque equal to better efficiency equal to higher power potential. If turbocharging is involved, lower compression allows more boost, which can produce significantly higher peak horsepower. So which is better? For naturally aspirated performance, higher compression wins. For turbo performance, balanced lower compression plus boost wins. Compression ratio alone does not create power. Power comes from pressure, airflow, and combustion control. Compression is a tool. How you use it defines the performance.